Okay, so this is example 2.1e, which corresponds to example 2.6 of your text. And the text is Statics and Dynamics by Gray, Costanza, Witt, and Plesha. And the title of the example is Addition of Vectors and Working Loads. And this is a really nice example to show how you can use vectors in ease to do a problem like this and make it maybe easier than doing it using pencils and paper. So here's the example, just to remind you. You have this post with an eye bolt screwed into the end, and you have these three cables attached to the eye bolt, and the three cables attached to these three forces, F1, F2, and F3. And we will need to add these forces to get the resultant force that's applied to the eye bolt. And then the other thing we'll do is figure out whether the eye bolt is likely to fail based on a maximum working load of 2,100 pounds force. Keeping in mind these working load multipliers that sit down here depending on what the angle of the resultant force is relative to the axis of the eye bolt. Alright, so this is a great one to start with in terms of using ease, because it gives us a chance to use some of the concepts we just talked about in terms of assigning and adding vectors. So let's go ahead and give this a try. So this is ease. The first thing I'm going to do in ease in my equations window is I think I'm going to go ahead and set the unit system, because I can see that there's going to be some angles involved in specifying these vectors. So unit system, degree, make sure that I know what units I should use for the angles as I'm assigning these vectors. And then the next thing I'm going to do is actually set up these three vectors. So there's three 2D vectors in the problem corresponding to F1, F2, and F3. So I'm going to declare three 2D vectors. So $vector 2D, and the vectors are going to be called F1, F2, and F3, just like that. And the next thing I have to do then is actually assign these vectors. So let's see. Looks like F1 I can assign using the vector assign polar command. You can see it's given the magnitude and the angle relative to the x-axis. So that one's pretty easy. Let's go ahead and do that one. So F1 is equal to vector assign polar. And because F1 is a 2D vector, I only need two arguments. The first one is the magnitude. So the magnitude is 200 pounds force. And then the second one is the angle relative to the x-axis, which in this case is 60 degrees. And maybe I'll give it a comment. This is the force of 1 on the eye bolt. And at this point I probably should solve. So calculate, solve. You can see that this is also accomplished using the hotkey or the shortcut key F2. And here's my my vector. Right, it's x component, y component, and units are pounds force based on the unit that I set here. If I want to, I can just right click on it and hit OK, and you can see the purple suggested unit goes to blue to say that that's the actual unit. So that's good. Let's move on to F2. So if you look at F2, they're specifying the magnitude of F2, and they're also telling you that for every 1 unit that it moves to the left, it moves 3 units up in the positive y-axis. So that's basically specifying the direction, right? So the way I'm going to do this then is I'm going to say F2 is equal to vector assign, and it goes, I guess, -1, 3. So that's the direction, -1, 3. If I'd like to turn this into a unit vector, I have to divide by the magnitude of that direction. So that would be what? The square root of 10, I guess, right? The square root of 1 squared plus 3 squared is square root of 10. So let's divide that by the square root of 10. That's my unit vector. And then to give it a magnitude, I'll multiply it by the magnitude, which is 500 pounds force. So this is going to be force 2. And again, before I move on, I'm going to go ahead and solve. In this case, I'll just hit the F2 key. And yeah, that looks right. It goes over to the left 158 pounds and it goes up 474 pounds. So again, let's set the units on that. All right, and then that brings us to F3. And you can see F3, they give us the magnitude and they give us the angle. In this case, they give us the angle relative to the negative y-axis. To use vector assigned polar, I need the angle relative to the positive x-axis. So I think that would be, let's see, if it's 70 relative to the negative y-axis, it would actually be 180 plus 20 is 200 relative to the positive x-axis, or equally well, it could be minus 160 relative to the positive x-axis. Each would be fine. So I'm going to say F3 is equal to vector assign polar, and this has a magnitude of 800 pounds, and these will always use pounds force, and either minus 160, or I guess again plus 200, it doesn't matter. So let's do minus 160 degrees, and this is force 3. So yep, that looks right. The components are in negative x and negative y, and all my units look okay. So the next thing I need to do then is add these together to get a resultant vector. So the resultant force is just the vector sum then of these three forces. So it's also a 2D vector. So the vector 2D directive, and we'll call our vector r, and r is just equal to f1 plus f2 plus f3, and that's the resultant. And we can solve, and this is our resultant force right here. If we'd like to know the magnitude and the angle of the resultant force, that's pretty easy. So we would say the magnitude of r is vector mag of r. So that's the magnitude. And the angle of r is equal to vector angle x. So this is going to be the angle relative to the x coordinate of that force. So that's the angle. And if we solve, we find that the magnitude is 892 pounds, and the angle is 155.2 degrees. That's relative to the x-axis. So if we want the angle relative to the axis of the eye bolt, we'd need to subtract off, I guess, 135 degrees, because the eye bolt is at an angle of 135 degrees relative to the x-axis. So let's see. What should we call this? Maybe theta. So theta is equal to, it would be angle r minus 135 degrees. So this is an angle relative to eye bolt axis, and looks like that's 20.22 degrees. So that can help us solve the next part, which is what is the allowable maximum load. So first we got to figure out the multiplier. So if we look at the range that we're in, we're between 0 and 30 degrees, which means that our multiplier is 60%. So let's put that in here. Our multiplier is 60%, and of course we'd like to convert that from percent to just a fraction so that I can actually multiply it. So this is multiplier, and the max load then is 2,100 pounds times the multiplier. So this is maximum allowable load. So turns out our max load is 1260 pounds, and the actual magnitude of the load is 892. So according to the criteria put forth here by the manufacturer, our eye bolt should be fine. We're not likely to fail. The solution using ease versus doing this by hand removes kind of a lot of the tedious work that might otherwise be associated with determining magnitudes and angles and so forth. And you need to know how to do those things, but sort of once you know how to do them, I'm not sure you learn a lot by doing them over and over again. So being able to solve this problem on a computer like this, I think really opens the door to you doing some more interesting types of problems and answering more interesting questions about each problem. So for example, we can answer some of the questions that were posed in the textbook, like what would happen if we were to remove these forces and only apply a subset of them? Would the eye bolt still be okay? So for example, maybe we want to understand if I were to remove force F2, would the eye bolt still be acceptable? So one way to remove any line of code is to highlight it the way I've done here, and then right click on it and just select comment. And that has temporarily removed the line of code that assigns F2. If I want to bring it back, it's very easy. You just highlight it and do undo comment, and there it's back again. So that's really handy in a bunch of situations. Here it's going to be handy because I can remove this line of code that assigned F2 and instead just assign F2 to be vector zeros. So that's the zeros vector. And so basically that's the same as me having now removed F2. So go ahead and solve it. And what you'll find then is that the magnitude of the force has gone down. It's now only 660 pounds, but it's at a less favorable angle. It's at 36 degrees, right? So if I go look at figure 1, because the angle has grown to be over 30 degrees, now I got to use a multiplier of 33%, right? So I would change this multiplier from 66 to 33%, and I find that the max load is 694 pounds, which is still a little bit higher than the applied load, but it's actually a lot closer to failure here, removing F2 than when F2 was applied, which is kind of counterintuitive and kind of interesting. So let's go back now and we'll reapply the original F2 and get rid of this. We can ask ourselves a question like, how big do any one of these forces have to get before we cause the eye bolt to fail, right? Everything else being constant. So right now, if I solve the magnitude of the resultant is 892 pounds force, and our max load is 1260 pounds force, so I'm well below failure. If I start to increase the magnitude of any of these forces, how big can I make it before this number grows to be equal to that number, right? And there's different ways of doing this. If I wanted to focus here on F2, I could just gradually increase F2. So let's make it 600 and solve. And you can see, that's gone up. I could make it 700 and solve, and it's gone up even more. So you can see how I can sneak up on the answer manually that way. Probably a better way of doing that is to just replace this magnitude with a variable. Let's call it mag of F2. And of course, if I try to solve now, it'll say that I'm underspecified, right? So I have to add an equation, and that equation is then the magnitude of the resultant is equal to max load, right? So this is basically our failure criteria. So now if I solve, what I should find is that ease is adjusting this variable until this equation is met, and it turns out that the magnitude of F2 of 968.5 pounds force is just where we hit our failure criteria, right? And our angle is still under 30 degrees, so our multiplier is still good, so we don't have to worry about that. But you can see how that's a nice kind of study that we can do very easily because we did the problem using a computer program rather than doing it by hand.